The way in which most students are introduced to calculus goes like this. You take a week reviewing some pre-calculus topics, make sure you understand the basics, and then start by learning limits. You learn what it means to take the value of a function as it approaches an x value, and what that looks like on a graph. You learn to add and subtract, multiply and divide limits. You learn to take limits of polynomials and rational functions, and root functions and trig functions, on and on until you get to the least understood concept in calculus, the precise definition of a limit. These confusing inequalities are often taught quickly and rushed past, leaving students confused and without an understanding of one of the most fundamental concepts in calculus. In this video, we are going to learn not only what this definition actually means, but also how to use it to find limits. Before we get into the inequalities, let's first get a hang of what the definition is actually saying. The precise definition of a limit is as follows. The limit as x approaches a of f of x equals L if for every epsilon greater than 0, there is a delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Before we worry about how to understand the inequalities, let's summarize the overall definition. We are saying that this particular limit of the function f of x exists if, for any positive number that you could pick, which we call epsilon, there is a corresponding other positive number delta, such that these inequalities are true. It might seem at this point that these two things couldn't possibly be related, but right now all we need to understand is that a limit exists if for every positive number, we can pick another positive number that satisfies the inequalities. So what are these inequalities actually saying? First, let's deal with 0 is less than the absolute value of x minus a is less than delta. We want to remove the absolute value. If the absolute value of something is between 0 and delta, that means that it is either actually between 0 and delta, or it's a negative number, and it's between 0 and negative delta. So we can say that x minus a is within these two intervals. Notice that these two intervals are almost intersecting, meaning that x minus a can be any value from negative delta to delta, except for 0. So let's write it as negative delta is less than x minus a is less than delta, and x minus a is not equal to 0. This turns into x is not equal to a. If we add a to both sides, we get a minus delta is less than x is less than a plus delta. What does this mean? If we graph this on a number line, where a is right here, we know that for a random delta, a minus delta would be here, and a plus delta would be here. And we are saying that x is contained within this range. And if we change delta, we can see that the size of the interval changes. Remember that a was the value in the limit that x is approaching. So what this inequality is saying is that we are looking at the values of x near where the limit is happening, and we can go no more than delta away from it. So we're restricting ourselves to this little range of x values near the limit. Now we can look at the other inequality. The absolute value of f of x minus L is less than epsilon. If the absolute value of something is less than epsilon, that means that it is less than epsilon and greater than negative epsilon, meaning we can turn that inequality into this. Negative epsilon is less than f of x minus L is less than epsilon. And if we add L to the inequality, we get L minus epsilon is less than f of x is less than L plus epsilon. And again, if we graph this on a number line, we can see that starting at L, we can go down to L minus epsilon and up to L plus epsilon. Now that we've done that, let's go back to our definition. We say that the limit as x approaches a of f of x equals L if for every epsilon greater than 0, there is a delta greater than 0 such that, and now we can put in our new intervals, if we choose x values that are close to a, then f of x will have y values that are close to L. How close? Delta and epsilon. So what we're basically saying here is that if you don't go more than delta away from a on the x-axis, f of x won't go more than epsilon away from L on the y-axis. This is very similar to one of the methods you learned at the start of learning limits. To guess the value of a limit, we calculate values close to x equals a, and therefore get values close enough to L to guess it. The problem with that method is that you can never choose enough points to be completely sure. Let's say we're looking for the limit as x approaches 0 of a particular function, and these are the values that we're getting. It looks pretty easy, that there's no doubt of what the limit is. Well, unless you said that as x approaches 0, the function approaches infinity from the left and negative infinity from the right, you ran into one of the problems with this method. What the precise definition of a limit says is that if we take x values close to a, all of the corresponding f of x values will be close to L. How close? Well, that depends on what epsilon you choose. No matter how restrictive or non-restrictive an epsilon might seem on the y-axis, there is a corresponding delta that will be able to restrict the function to a certain range on the x-axis. It creates a sort of box around the point where the limit is, and states that if the limit exists, it will not leave the box over this interval. We can see that there is no size box that will contain all the values of the function, and therefore we know that the limit does not exist. Now that we understand how this definition works, let's show how to use it. The basic idea behind this method is that we want to create a formula for delta that contains epsilon, meaning that for any epsilon we choose, we can just plug it into the formula to get delta. Let's prove that the limit as x approaches 3 of 2x plus 2 is equal to 8. Let's define our variables. A is the value that x is approaching, so it's 3. F of x is the function that the limit is evaluating, so it's 2x plus 2. And L is the value of the limit, so it's 8. Plugging them into our equations, we can see that 0 is less than the absolute value of x minus 3 is less than delta, and the absolute value of 2x plus 2 minus 8 is less than epsilon. We can ignore the 0, since we know that an absolute value isn't negative. The only thing this is saying is that the absolute value of x minus 3 isn't equal to 0, which means that x isn't equal to 3. But we're looking at the behavior of this function as it approaches 3, not actually at 3, so this restriction doesn't matter. So if the absolute value of x minus 3 is less than delta, and simplifying the other inequality, the absolute value of 2x minus 6 is less than epsilon. We want the left sides of both equations to match. So let's factor out a 2 from the second inequality to get 2 times x minus 3 is less than epsilon. Since 2 is positive, we can factor it out of the absolute value. And then, dividing both sides by 2, we get the absolute value of x minus 3 is less than epsilon over 2. And now, since the absolute value of x minus 3 is less than delta, and it's less than epsilon over 2, we can say that delta is equal to epsilon over 2. And therefore, since we have a delta for every possible epsilon, we have proved the limit. If you have any questions or requests for other videos, let me know in the comments below. Information on homework help and tutoring is in the video description. Thank you for watching.